of calculations of index of refraction, hopefully enough so that you'll get sick of it. And by sick of it, I mean bored to the point where you actually know it and how to do it. But before we do any of the index of refraction stuff, let me go over a few grade updates that we've got. Yesterday, I took most of the day to get our classwork clicking scores up to date and posted. Now, everybody's got something like this. If you order by assignment, or if you arrange by assignment group, you'll see classwork scores total, classwork pointage as of 11/07/19 at the top of your grades page. All right. Now, the raw data from clicking is 102 points possible. All right. So this hypothetical student answered 88 questions correctly. All right. Now that's everything up to Wednesday. All right. We've had 102 questions, and this student answered 88 of them correctly. All right, now you can look at yours and see how many, and then all I do is I convert that to some fraction of 36. So I take 88 over 102, and then I multiply by 36, and then I round up to the nearest whole number, in this case 32. Okay, so your points for the semester, if I were going to do, if I were going to do semester grades right now, it would be 2 midterms, 84 points, plus 36 points for classwork, plus 36 points for homework. Now, I didn't make a diagram or a slide of the homework, but it's a little bit further down the page, and it's similar. So that's a total of 156. Okay. And so, so you could, you're going to have, like 123 out of 156 as of today. Now, by the end of the semester, it'll be up to, I think it's 240 for our total. Let's see, 156 plus 80, 240. Yeah. So, but the other thing that's in here is that, well, the other thing that's in is a few of you have some bonus points. Now, I haven't done the exam 2 bonus points yet. I'll probably do that this weekend. I'll finish it and post it. But you have some early iClicker bonus points and stuff. But so right now, this is what you want to focus on, this one, and then the similar one for homework. And then you know what your exam grades are. Now, I want to point out something to you. I also calculated letter grades as if I were going to give out letter grades today. So this is where everybody stands. This is as a group. This is the curve. All right. So, but I never do curves. Okay. If you earn it, you got it. I don't, try to manipulate scores or anything. So we have a few A's and we have 1 F. Everybody that's been taking exams and doing homework is probably either D, C, B, or A. Only one person has got an F right now. Ton of B's and C's, as you can see. Only 2 people have A's. Now that's going to change by the time we do exam 3, and again at the final exam, because we have a lot of points coming up, and the reason it's going to change after exam 3 is because then we do the maneuver with your scores, keep the best 2 out of 3 midterms, drop the lowest. Now they'll still be in web courses. I don't erase them from web courses, but when I do my calculations, I'll post your best 2 out of 3 figure in web courses, although all 3 exams will still be in there. And some of you have made comments about, well, Dr. B, why can't I see my grade in web courses, like I always do in my other classes? And that's because the grading scheme in web courses is extremely simple. They can't handle any kind of deluxe grading procedures at all. Okay, so I mean they can't handle the fact that we have 102 points for clicking and that it's scaled down to 36 points. They can't handle that. So I do that all on a spreadsheet, and then I upload columns of the spreadsheet into the grades, and then activate that, and you'll see it in your. So your grade, basically the grade book and web course is static, and you can't hardly do jack with it. It's pretty bad. So I turn off all those automatic grade things that they have that you may see for your other classes. You know, like down at the bottom of your grades page and stuff. Actually, let me see if I can do this here. Can you? Well, I'll do it. Let me just show you here. Okay. Let me pull this out a little bit. Come on, baby. No, I just want to make it a little bit bigger. Okay, I'm going to go to student view here. Okay, so here's the student view. This is pretty much what it looks like for you guys. And grades. Okay, so here's the same stuff. Now, right here, it says total points as of 11/7/19. All right, now that's not on the PowerPoint, but it is on your grades page. That's the one you look at. So this student, this hypothetical student, John Q student, has 120 out of 156. Okay, and so then we would go and look at the grade scale. Now, let me switch back to the PowerPoint, to the Keynote files. To look at the exact grade scale, you can go to discussions. I put up a thread on that yesterday. So, and you can ask further questions, but let me admonish you to avoid putting your own personal grade numbers in the discussions area. So if you have a question, go ahead and ask a question, but don't put well, my exam grade on number 2 was 41, or whatever it happens to be. Don't put that in, because that violates the feds. The feds would come after you or come after me. So if you do that, I always delete it. So just don't do it. All right. It's the way things are supposed to go for privacy. Okay, you can get this thing back. All right. So if you have any other questions, we're going to, I'll just refer you to discussions, ask your questions there. Okay, last time. Do you want to fix this now? Last time we were talking about reflection and refraction. The diagram here shows the basic idea for reflection off of a surface, off a reflective surface. And this is for flat or well-ground surfaces. If you have something that's rough, you get something called diffuse reflection, which you're looking at. Everything that you're looking at here is diffuse, except for maybe the glass in the window or in the door frame over there. But everything else, and even your computer screen, I don't think has a flat enough surface to really have good reflection. Maybe it would. But anyways, flat mirrors, this is the law for a flat mirror. But remember, when we do concave, we also consider each small pixel of a concave mirror to be a flat mirror, and then we use the 3 principal rays plus 1. And we did an example. Here's an example for the concave mirror. All right, those are in Instagram. Now today I don't have my cell phone with me. I left it at home, so I can't do Instagram. But I have something even better than that. I have some special PDFs that we're going to use on the document cam. But anyways, this is from the document cam on Wednesday. And from that, we located position of the image And also we were able to figure out from the diagram the sense of the image, whether it was upright or inverted. And in fact, from that, you can see that the image is shrunk down a little bit. It's actually a little bit smaller than the object. Now, if I had the object in a different position between C and F, it'd be completely different. Okay. If I had it between F and S, completely different. But you just do the tracing of the rays, figure out where the image is, and let the chips fall where they may. Or should I say, let the photons blaze where they may. The formula we use is a shorthand. It's an approximation, but it's pretty good for government work. 1 over F equals 1 over D object plus 1 over D image. Okay, and we used that in a couple examples for the concave and the convex mirror. And I'll refer you to the YouTube of session 31 for that. And we did some calculations of image distance on Wednesday. And since we did that calculation in lecture, there's a high likelihood that on Wednesday next week, you'll see something like what we did in lecture. You know, now I'm not telling you what's on the test, but I will just say there's a high, because I haven't written it yet, but there'll be a high likelihood for that. All right, now what I want to talk about today is total internal reflection, which involves refraction. Now here's just a few blurbs of what we were talking about last time about refraction. Snell's law of refraction, it's based on the fact that different media have different speeds of light. So light propagates through glass at a slightly different speed than it propagates through water, and slightly different again than it propagates through air. And that's measurably different, very slightly different from the speed of light as it propagates through a vacuum. Okay, vacuum, it's, 3 times 10 to the 8. Everything else is a little bit different, sometimes quite a bit different. Now, the material medium that has a very high index of refraction, you know what it is? Diamonds, carbon crystals that you have on an engagement ring and stuff like that. And the other one is cubic zirconium, has a very high index of refraction. And you can read about how it makes things sparkle and stuff, but I'm not going to dwell on that too much. I mentioned the marching band analogy. There's also a nice lawnmower. Go ahead and make a note. The lawnmower analogy in this section on refraction in chapter 25. Now we're going to do a calculation here with Snell's law. Okay, no, with a definition of index of refraction. All right, so let's just go back in your notes, look up the law, the rule, the formula for index of refraction, and go ahead and turn on your computers and get ready to type in a numeric answer. Here we go. The speed of light in medium 1. Okay, that's the pink stuff. It's 2.0. Oh, what the? That says 10 of the second. It's supposed to say 10 to the 8. So rub that out in your notes. Rub that out. 2.0 times 10 to the 8. I can't believe it. How did I mess that up? When I typed that in, it's in LaTeX. So that's all right. So these, I'll correct it for the YouTube, but make sure you have 2.00 times 10 to the 8 meters per second. And the one down below, medium number 2, is 2.25. We'll do that in a second as well. Go ahead and calculate your index of refraction to 3 significant figures, please. So it's going to be 1 point something something. Is 1 a significant figure when you're talking about index of refraction? I suppose it is. Because, what do you think? Is 1 a significant figure in indices of refraction? Yeah, 1 point something something. You would? Because some things are bigger than one. So there's, yeah. All right. So this is what I'm asking for. So something with 2.85, that's even more than diamonds. I suppose there's stuff that has that, but I don't know what it would be. You guys go ahead and circulate around. I can't believe it. Dr. B. Okay, I'm going to pause this. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Um, yeah, this is looking pretty good. The index of refraction is 1.5. So now that's for this medium up here. Here's the calculation. A few of you got it wrong. There it is, just 3.00 divided by the speed of light in medium 1. All right, now let's try another one. Let's do medium 2. You guys ought to be able to do this in about 20 seconds. Okay, 20 seconds starting right. No, I'll give you a little more time than that. And notice that I got the exponents correct now. 10 to the 8, 2.25 times 10 to the 8. You what? Really? Yeah, these are supposed to be radio frequency like little cell phones, so you don't have to aim it at the thing, but do you have good batteries in there? Do you have good batteries? Yeah, but are they good? But are they Duracells or are they the cheapos that it came with? Put in some Duracells for the rest of the semester if you got any at home. Energizer, something good quality. Because those ones that they put in to sell it to you are the cheapest that they can get. So they have a nasty habit of flaking out in the middle of an exam because you have it on for such a long time. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Go ahead and make a count, please. Um, Raise your hand if you got this, 1.33. Good, good. All right, so there's the, oh, I see some 1.3s and some, okay, we better do some splaining on this. Okay, be, shh. If you want to get an A, you got to get it right. Because something like, Something like this, I might put on a multiple choice. So you're going to have to figure out which one. And if you go around looking for 1.33 and you don't see it on the list of multiple choice, then what are you going to do? Right? 1.34. Then what are you going to do? Okay, so those are wrong down there. You got to be careful. All right. Now let's go to the next slide here. And here's the calculation again. Jot it down if you got it wrong. And you can see, let's break this down. This is 12 over 9. 12 over 9. That's 1 3/9. So 1.333333 repeating for this. So to two significant figures, 1.33. All right, now let's talk about Snell's Law. Go ahead and jot this down in your notes for today. We're going to use it out the wazoo. All right, we're about to embark on a big, ginormous session of calculating angles of refraction, indices of refraction, and assorted things along with that using Snell's Law. So, and what we're going to do is we're going to go to the document camera for some refraction calculations. And what I'm going to do is use a special kind of PDF, a special kind of notebook paper that I call talking PDFs. It's basically developed for people with hearing handicaps, technology developed for people with hearing handicap, but it works great for it's great for anything, great for anybody. So let's go to the document camera and be ready to change my slides here. Let's go to this one. Actually, let's go to this one. Switch back to laptop. Okay. All right. Go ahead and switch to document camera. Okay. Now, hopefully this works. Here's my notebook of special graph paper, and you can see that I've got a lot of different Whoa, Physics 2053 last January. Hey, some of you guys were here for this one. Right, so you guys remember. Velocity graph, 4 points. Honda Prius versus Escalade. Speeds. Oh, that's the skier flight test. Remember that one? Airplane. Okay. Now this is special graph papyrus. And I'm going to refer to my notes. Could you bring that stool over right here? Okay, let me just put it right here. I'll put my notes here. That'll be good. I now have 3 mics on me. And of course, this one's all tangled up. Okay, here's my special pen. And just so you know, this thing, it's kind of hard to see here with all the glare, but it has a regular ink pen up here. Well, it's probably a special ink, blue ink. And it has an opening here. And inside that opening, you can't really see it, there's a little infrared camera. that records everything that I do. And then when I am done with it, I save the pages, and then I export them into a PDF that has an audio file attached to it, so that you can listen to everything that I say. So the way to start it, let me put on my specs. I'm mic'd up 3 ways from Sunday here. See this down here? These little icons? All I have to do is, whoops. Okay, I'm recording. Let me stop. Okay, here we go. So physics 2053, and you'll see this writing unfold on the PDF in front of your eyes. Now let's do a little index of refraction calculation. Could I do what? I wonder if the freeze. All right. All right. So here's my interface. Here's my surface. And let's say that up here, n is equal to 1. It's air. Okay, and then down below, I'll call this N2. Let's go 1.6 for the index of refraction for substance 2. Let's make this N1 up here. All right. Now, in the middle of my surface, I'll draw a normal as a dotted line. Okay. And then I'll draw a ray coming in, right like that. Okay. And then it's going to slow down. So this is V is equal to slower than C over here. So this is going to turn towards the normal. So what I like to do, my incoming, I like to just keep running it out. Now that's a fiduciary line to guide me in my outgoing ray. My outgoing ray, or I should say my refracted ray, is going to be a little bit steeper than that. All right, because it's gonna slow down, just like the marching band. So I'm going to dip in about like this. Now this is my diagram, and we're going to let the numbers do the talking. So this is theta 2 over here, and this one's theta 1. All right. Now if I specify that theta 1, that's my aiming angle. If I say that that's equal to 34 degrees, then I could figure out what theta 2 is. Okay, so that's our objective. All right. So the way that you set this up is using Snell's law. So N1 sine theta 1, that's the stuff on top, equals N2 times the sine of theta 2. All right, now this is a 1.00. And then over here, I have the sine of 34 degrees. And that's equal to, okay, N2 is 1.6. I'll put parentheses around that. And then sine of theta 2. So this doesn't give me theta 2 directly. It gives me sine of theta 2. So I'll get the sine of theta 2 and then do inverse sine of that. right? So now sine of 34 is, what's the sine of 34? This is equal to what? 0.55, two more digits. 9 what? 91? 92, round it off. Okay. So 0.5592. Anybody verify that to 4 significant? Okay. All right. So basically, I've got the numerator 0.5, and I've got this 1 out here, so that's pretty easy to deal with. In other words, I don't have to deal with it. So here's my numerator, and that's a sine and an index of refraction. And then here's my other index of refraction down here in the bottom. And that's equal to the sine of theta 2. And that works out to, anybody verify me, 0.349496? Anybody verify me on that?
Yeah.
All right. So theta 2 is the inverse sine of that. So sine to the minus 1 button of 0.349496. And that is equal to, what do you get? 20 point something? 20.46, that's what I got. Okay, and that's degrees. And so now, even though if I take a protractor to my diagram, I might not have 20.4. I might not even have 20 there. 20 anything, 22 or 23 or anything. It might be, this might be, like 17 degrees. But it's enough that it breaks toward the vertical. So it doesn't, so this little dotted line, I'll just put the word no. The refracted ray does not go along that same steepness angle, right? It bends to this, it's a little bit steeper now. And when you let the numbers do the talking, you get 20.46, okay? Now, let's do another one. Let me stop. I'm not getting any, I can't really hear this, but yeah, that stopped. All right, now I'm going to go to the next page. We're going to do another calculation. Whoa. Boy, I hope that doesn't mess things up. Okay. Now let me start. Okay. Now this one, let's do a surface that's at a slant. Okay, so here's my surface up here, okay? And up here, I'm gonna have water. So N1 is equal to 1.33. That's the specific, or that's the index of refraction for water. And then down here, I'm going to have air again. So now N2 is equal to 1.00. Okay. Now, I want you in the middle of your line segment, go ahead and make a perpendicular. So there's your normal. And here's the place where my ray is going to come in. All right, right there. Now, right up about here, kind of above it and slightly to the left, I want you to put a dot right here, and we'll label that C. Okay, so my ray, now this time I'm going from water out to air. But I'm gonna aim it right at this point here. All right, so there's my and so here's theta 1 right here. All right. Now I'm going from slow into fast. So that means that instead of keeping, oh my goodness, this is really pathetic. Okay, this is better. So instead of going this way, no, it doesn't go that way. It's going to cut a little bit away from the normal. So it's not going to go straight through. It's going to cut, and I'll make a solid line here. It's going to cut something like that. All right, so there's my outgoing ray. Now, I've got a bunch of lines in here, so I'm not going to write in theta 2, but you can sure do that if you want. All right. And let's just run this out here. And we'll put a point here, U. And yeah, okay, so that's good. All right. So there's my ray. Now, let's figure out N1 sine theta 1 equals N2 sine theta 2. All right, and we're going to try to get theta 2 again. All right, so N1 in this case is 1.33. And let's say that theta 1, I'll write this over here. Let's say that theta 1 is 35 degrees, just for a nice round number. Okay, so this one up here, I don't know if it looks close to 30 up there. It's not too bad. Okay, so sine of 35 degrees equals, okay, now N2 is just 1.00, so that's going to be easy. Okay, so now we have the, whoa, what happened to that thing? There it is. It keeps, oh, that's what you were trying to tell me? Can you call, there should be a sticker here that has the number of OIR. What about the sticker in the corner there? Let's okay. See if it's, go tell Ray, go around and tell Ray that this thing's flicking. Tell him to call OIR. They'll come and fix it. Just needs a new fuse or something. All right, so here's our calculation again. So the sine of 35 is 762,857, correct? All right. So we have 1.33 times 0.762857. And you guys, you can use as many digits on sines as you want. Oh, wait a minute. Yeah, right. Okay. So I've got it up here. 1.33. Now here's the sine. 0.57. 3576. There we go. Equals, okay, so it's basically sine of theta 2. All right, so sine of theta 2 is the product of those two, so 0.762 0.857. Johnny, you verify me on that? Okay, so that's the sine of theta 2. And so theta 2 is the inverse sine of 0.762857, which means theta 2 is, okay, what do you get, 49.7? All right, 49.7 degrees. And so that's this, boy, I wish I could, all right. Let me extend my ray out here this way. Okay, so here's 49.7 degrees all the way out to here. Okay. And so you can see that it swings away from the normal. Question? Yeah. I'm on the exam. There'll be a small table. If you did your reading, you saw this last night. There'll be a small table of indices on the cover page. Okay, so don't worry about that. I always have to look them up myself, so I don't expect you to do something other than that. Okay, so that's from slow to fast. Now, next one I want to do is, so this is number 2 for today. This is number 3. This is an unknown substance. So this is how you would figure out the index of refraction of something. So let's do a vertical or a horizontal surface this time. Oh, by the way, let me go back up here to number 2. This point U here, that stands for you. You are here. You're looking at point C, but the way that this works, this ray comes in here to the interaction point, and then it refracts through point U. Now that's you. That's your eyeball there. So for you, the stuff that's in the water appears to be back over here at this, right about here. Okay. Now let's call that capital T. All right. So object C appears to be at point T. And guess what that's like? That's the headless body. Here's the head, C for coconut. Cranium. Here's point T, torso. The headless body. His body appears to be over here. His coconut is above the water, so you see it directly. It's over here to the left. So this is how it works, and this is you down here. All right, so this is the headless torso problem. And if you look at that image, you will, and I embedded it in the textbook in one of my annotations. You'll be able to see the headless torso photo. And I've got it set up very similar to what is in the photo. This is like an overhead view of the headless torso photograph. And this is how it works. All right, now, next problem is to identify an unknown substance. So here's my surface. And let's put a normal to the surface. And let's say that I've got water here. N1 equals 1.33. And down here, I don't know what N2 is. So that's a question mark. Okay, but we want to figure that out. And what we can do is measure angles in the lab. So 45 degrees. So there's my theta 1, 45 degrees. And let's say that it comes out. Okay, so here's my 45 degree line. Nope, doesn't go there. It's going into a slower medium because it tilts a little bit in. So here's my refracted ray. And this is theta 2. Right? So we can measure that. Theta 2 measures 40.3 degrees. Okay, so you're in the lab and you can't aim the beam of light, like your laser at theta equals 0. You don't want it to go straight into the water perpendicular to the surface. So another easy angle is 45. So you aim your laser at 45, and then you look for the outgoing angle. You figure it out using trig and everything like that. It's 40.3. Okay, what does that tell you about N2? Well, let's set up Snell's Law. N1 sine of theta 1 equals N2 times sine of theta 2. Let's plug in what we know. Now we don't know N2. This is my question mark here. So we're going to figure that out. We've got N1, that's 1.33 for water. And sine of theta 1 is square root 2 over 2. And that's equal to N2 times the sine of 40.3 degrees. Okay. And so let's see. So N2, let's get this N2 by itself. N2 is equal to this quotient, 1.33 times square root 2 over 2. That's the sine of 45. Divided by the sine of 40.3, which we have to use your calculator to look up. Okay, who's got an answer for this calculation? Huh? 1.5. Give me. I've got 3 significant figures for my angle, so give me 3. 1 point something something something. 1.454. Okay. Now look up on the table of substances. In the textbook or on the cover page. This is actually a problem from the book, right here, this unknown substance. And the unknown identity is fused quartz, which, Kendra, do you use optics made of fused quartz? You know what I'm talking about? Fused quartz is a kind of a optical material that they use for certain kinds of optics. I'm not sure why. You know, there's all kinds of different glasses that they make for optics, including silicon, which is not glass. I mean, but they use it for infrared optics. Okay, so there's your unknown fused quartz. Go to the next page. Okay. Now I'm going to do a special. Let me stop this. Okay. I'm going to do a special calculation now. With 2 material media that So this is going to be close values of n. All right. So I'm going to put my surface here. And my normal perpendicular. And we're just going to trace one ray. Now we're going to start down here underneath. So down here, let's write down N1 equals 1.667, right? And up here, N2 equals 1.523. Now this is possibly two different kinds of glass, because that's about the index of refraction area for glass. You know, the one we just did was 1.454. That's quartz is a kind of a glass. I mean, it's not glass, but they make they make optics out of it. It's like it's a transparent material that they make optics out of. Anyway, so here are my two specific. Now let's aim my incoming ray at 30 degrees. All right. And let's continue it. Here's my dotted line. If there was no such thing as refraction, this is where it would go. But we know it doesn't go that way. So it's going to refract. And it's going to refract away from that no line to the left or away from it to the right. It's going to get steeper or it's going to get less steep on the way out. Now, let me ask you this. Which one is faster? The speed of light is faster in which medium? Number 1 or number 2? 2, because it's closer to 1. So this is the faster medium. Okay, and you can calculate the speed of light in that medium if you want. I think I actually did it. It's 1.97 times 10 to the 8 meters per second. And down here, V1 is 1.80 times 10 to the 8. Now, we don't need those speeds except to think about which one's faster and which one's slower. Now, if it's faster, it turns away from the normal. So my outgoing ray is going to be somewhere over here. So I'm going to exaggerate it a little bit. Okay, so there's my outgoing ray. Okay, now that's a little exaggerated. And now we're going to let the numbers do the talking, right? So incoming at 30, and this angle here is what we're going to calculate now. This is theta 2. And let's go ahead and do it. N1 sine theta 1 equals N2 sine theta 2. Okay, N1 is 1.667. And sine theta 1, sine of 30, that's 1/2. That's an easy one. And sine theta 2 is what we want to figure out. So we've got 1.523 up here for the faster medium. And so sine theta 2. So sine theta 2, theta 2 is going to be greater than 30. It better be. We better come up with, like 30 something or maybe even 40 something degrees. Probably not much more than that. All right, but let's figure this out. All right, so here we go. 1.6 1.67 times 1/2 and divide both sides by 1.53. So here's my quotient, 1.667 times 1/2 divided by 1.523, and that's equal to the sine of theta 2. And so the sine of theta 2, so what do you get? 0.54728 for this quotient? Okay, so I'll write it over here. 0.54728. So theta 2 is the inverse sine of 0.54728. And that is theta 2 equals 33.18 degrees. Okay. Now, students, if theta 1 now is steeper, let's make it 45 degrees. All right, that's another nice easy number. Then theta, whatever else you know, theta 2 is going to be greater than 45, i.e. even steeper. And you can calculate it just the way we just did. Okay, so that's going to be a little bit steeper than 33. So it's going to might be 48.2 or 49.7 or whatever it works out to be. That might be a nice exam problem. What's theta 2 for this calculation here? But whatever it is, it's going to be a little bit bigger than 45. So as this angle, as theta 1 increases, theta 2 gets bigger and bigger, closer to 90. All right? And that, my wonderful students, is what total internal reflection is all about. So let me just jot this down. And I'll just remind you, let me make one little addition to my upper diagram here. For this surface between these two kinds of glass, there's going to be some reflection. So I'm going to try to draw with dots here. Here's the outgoing reflected ray. So there's a little bit reflected and a little bit refracted. Okay, and that usually happens, at most interfaces. You'll get a little bit of reflection, it'll split, and there's ways to calculate the split, but we're not going to get into that, except for the fact that we're going to now talk about total internal reflection. All right, now let me stop my talking PDF. Okay, and let me take this off. And I think I'm done with talking PDFs for today. Can you take this? Set it up over there. All right. Oh boy, I recorded all that. Well, you just recorded, I just recorded everything on the YouTube. That's all right. So I'll embed the PDFs in the YouTube, and also you'll have the talking versions that work really nice. Okay. Let's get back to work here. All right. Now, here's what we're looking at. What we just did was this calculation here for a fiber optic cable in which N1 is 1.667. All right, now that's what we had down in the lower part of the diagram. That's why I made, and so if you look at the cross-sectional view of fiber optic, the core, this greenish area, is going to have a slightly higher index of refraction. Now, this stuff out here that surrounds the core is called the cladding. C-L-A-D-D-I-N-G, the cladding. And the cladding has to have a little bit smaller index of refraction. It's got to be a little bit faster medium. Right now, the way that they do this is with two different kinds of glass. You know, it's got to be flexible. It's really tough to do, but they've got a lot of good optic fibers, of course. Now, here, down here is the actual. All right, here's these line segments are at the actual tilt angles. Now, the diagram that I put on the PDF is kind of floaty. It's not very precise. These are. All right, so here's a side view of it. And you can see that this thing at 33 degrees, it's almost straight. All right. Let me ask you a question. A mental IQ test question. At what angle theta 1 would the refracted ray, go in exactly the same, not almost straight, but perfectly straight? At what incoming angle? See, Cassidy, I'm trying to get you to think. What angle? So if it comes in at 30, you get a 3-degree bend, right? What angle do you have to? Does it have to be smaller or bigger than 30? No. What angle will the outgoing angle be exactly the same? You know, like 18 and 18. What angle would that be? What do you think, Danny? What do you think? Yeah, 0. When it's going straight up. Straight up, it doesn't refract. Is that what you guys are thinking? No. Yeah, straight 0, straight up. I heard all the over here to the left. I heard. I didn't hear the rest of it, but I heard him using the letter Z, so that's why I called on him. Anyway, so yeah, 0 if it was going straight. So if we increase, as I said before, if we increase theta 1, there's going to be a bigger and bigger bend. Write that down. If you increase theta 1, you're going to get a bigger and bigger bend. I mean, that's what refraction does. It bends light. That's how eyeglasses work, and raindrops that form rainbows. Okay? So if that angle gets bigger and bigger, you get a bigger and bigger bend. Okay? If it gets steeper and steeper, smaller and smaller, it goes from 33, that's a 3.18 degree bend, to smaller and smaller, and eventually 0 when it's going straight up. Okay? All right. Now, I have a clicker question for you. This is multiple choice, so hit the refresh key. Let me get my... All right. Hit your refresh key and then answer this question. Oh, actually, hold on. It's short answer. So type in a letter and hit the send key. Give me a letter, A, B, C, or D. And actually, I already told you the answer just about 5 minutes ago during the talking PDFs. So give me a letter and then hit the send key. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Uh-oh. We got some splaining to do. Refraction. What's the physical reason that light refracts? Because what is true? Speed of light is different. Okay, so B is correct. But well, wait a minute now. Wait a minute now. Wait a minute now. Well, hold on to your horses. Do you have a comment to make? D is the same thing, so that's correct too. Geniuses. So if you asked, if you answered either one, let's see, 45 and 40, 91%. All right, so the rest of you, yeah, that's why it is. Okay. So a few of you answered A and C. You know, look at that. The wavelength effectively doubles. Do not let me tempt you. Because, you know, the wavelength does change for refracted light. The incident and the refracted wavelengths are different. Both kinds of glass are transparent. No, there's no differentiation in that statement. So that one should, you know, you should look at that and say, why does anything happen? If they're both transparent, and if that's the reason, why does anything happen? The answer is they are both pretty transparent. They're both glasses, but they have slightly different indices of refraction because the speed of light is very close to being the same in both. So, so yeah, you guys are doing good today. So if I put a lot of these kind of questions on the test, you'd be in favor of that? Okay, so a lot of total internal reflection. Yeah, okay. All right, so here's one of my famous jukes. Heidi, you almost she was in an uproar over here. But see, that's good. That's good because you were fighting for what you thought was correct, and you actually were correct. Yeah, and you're correct. So, and the reason for that is you know, basically just look at the definition of index of refraction. If n is different, that means v, you know, c is a constant of nature. So if v's are different, n is different, and vice versa. All right, now let's get back to our table here. Go ahead and make sure you write this stuff down because it's important. Now here's another interaction. And the down here at the bottom, where's my, okay, down here at the bottom, that is precise. So 45 degrees, and you can kind of see that this incident angle here is 45 degrees. This one's a little bit further away, 50 point something, 50.711. And you guys, you can jot these down and you can just verify, you know, for homework if you want. I've done them for you. And that diagram there is precise. All right. Now let's try another one. 60 degrees. Whoa. I'm making my incoming ray a little bit bigger angle of incidence. And the outgoing ray, whoa, 71. That's a bend of 11 degrees. In the 45 degree ray, you got a bend of 5.7 degrees. 30 degrees, you only got 3 degrees of bend. This one, you've got 11 degrees of bend. All right, 65. Whoa. 65 That's 17. That's almost 18 degrees of bend. And that diagram, again, is precise. All right. And you can continue with a table like that. It's fairly easy to do. All right. Now make sure you have this table. And you can verify all these things. You know, we've already done a ton of questions, a ton of calculations. Now, instead of a table, here's a graph. Basically the same thing. And so you can see it starts to get really bigger and bigger. So look down here at 30. At 30 degrees angle of incidence, the outgoing angle is up here is 33. At 45, your angle of refraction is a little bit bigger. Now look it up here at about 60 something, you get close to 90. And that, my wonderful students, is an angle we want to figure out. So for instance, here's another level in the table. At 66 degrees, you're starting to really bend it. That's 23.28 degrees of bend. And my diagram is accurate. Now I made that outgoing ray really thick so that you could see it. It's a little bit, it's just skimming, just bit, it's not even a degree off the surface. All right? Now, for all of these things, there's some reflection. Now, I didn't draw in the reflections, but it's in there. This one, you're going to have some reflection, and you're going to have some refraction, and the refracted ray going off to the right is just barely skimming the surface. All right? Now, total internal reflection is the angle at which refraction ceases. This is the condition for it. N1 sine of some critical angle, theta subscript c, is equal to N2 times the sine of 90. 90 is my refractive angle. When that's 90, I don't get any refraction. It's not going anywhere. It's absorbed by the surface. It doesn't even go in the surface. It doesn't re-emit out to the other side of the surface. It's all going to. So if you go a little bit above theta c, you'll have zip zap. You'll have no refraction, all reflection. All right. So let's work this out. All right. So N1 times the sine of your critical angle is equal to N2 times 1. Now the sine of 90 is 1. That's an easy one. All right. So the sine of theta c, sine of the critical angle, is simply the ratio of N2 over N1. Right? Now N2 is your faster speed. It's going to be your smaller index of refraction. Okay? So make a note. That's small index of refraction divided by big index of refraction. All right? And that's going to be a number less than 1. Small divided by big is, 0 point something, something, something. All right? So you can do the inverse sine of that. Okay? And that's your critical angle. So total internal reflection begins at this angle. So if you have an optic cable in which you can restrict the rays going in to this or bigger angle, it'll all be contained by the cable. All right? Now, let me see if I have another calculation to offer here. No. Um, um, so instead of dot cam examples, let's go to the chapter on total internal reflection here. Okay, I'll just switch it. All right. Oh man, I gotta go way down here. Dude, why are these all open? La, 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 la. Here we go. Oh, look at this telescopes. We got to do some of that when we get back from exam 2 or exam 3. Okay, here we go. Okay, total internal reflection. Oh, look at this. I got a bunch of, annotations, if you please. Oh, a diagram, if you please. Yeah, this is a really nice interactive. Here's an image of it over here to the right. Okay, where's my cursor? Okay, over here to the right, right? Oh, let's see what my next annotation is. Reflected. All the light is reflected. 100% reflected. So that's what happens with, here it is. Here's total figure 1. A ray of light crosses a boundary where the speed of light increases and the index of refraction decreases. N2 is less than N1. The ray bends away from the perpendicular. Critical angle is the one for which the angle of refraction is 90. Whoa, that's missing. Look at that. I'll go in and insert that. Now let's go down here and look at some of these diagrams. Okay, so here's basically, this is how a fiber optic cable works. It just ricochets off the inner surface because it can't penetrate. Now, if the light comes in along this angle. Now you can't bend them. You can't bend these cables larger than a certain radius of curvature. Okay, but they are flexible. They're just not infinitely flexible. But anyways, if you do that, the light will just go through here, and you could use it. You know, it's like looking through a straw. You know, if you have one of these, you can see around corners. You know, but of course that would you'd have to have a fiber optic cable as big as your iris, or a bundle of fiber optic cables, and then the bundle as big as your iris. And guess what that is? A bundle of fiber optic cables? That's called an endoscope. I think they got a diagram of that down here. There it is. You're looking at somebody's trachea here, I guess. Okay. And it's pretty disgusting looking, but so here's the term cladding. But yeah, that's what an endoscope is. All right. Now let's go back to laptop. Okay, so I'll put an image in here instead of dot cam. I'll put in an image of a fiber optic cable. Okay, now we're done with instruction for today, but now I want to give you some exam comments for exam 3. All right. So this is like your homework assignment for the weekend. Now, the furthest extent that we've gone is 25.4, total internal reflection. We've done several bypassed sections, though, in chapter 23. And I haven't marked all of them as bypassed the way I do sometimes, but I'll try to do that this weekend. We skipped an awful lot of stuff in chapter 23. We could have, if we hadn't had a hurricane, we might have done all that, but I had to cut that out. So I'll try to mark the bypass sections of chapter 23. Now, the other thing that's not, it's kind of out of the ordinary is we dipped ahead to chapter 27.9 on polarization. And we didn't do a whole lot, but we did do a demonstration of that. And the demonstration, my wonderful students, is going to be on the exam. So make sure you try to remember that demonstration of optical rotation. And if you weren't here for that, just type it, go to YouTube and type in optical rotation. And there'll probably be some, some demonstrations kind of like what we did, right? Probably even better, all right? Now, that's all from the textbook. Oh, and by the way, chapter 24, I think we pretty much covered most of that, all right? But if I annotate it and stuff, consider it fair game. And if it's, but really concentrate on what we do in class. So, and remember so don't go like memorizing the textbook. I mean, don't worry about memorizing at all. I was talking to a student yesterday, and the student said, this class is different from the classes that I'm used to taking, like anatomy and life sciences classes, where you do a lot of memorizing. And in this class, the way I explained it is you want to be able to put together two disparate ideas, one from chapter 27 and one from chapter 23, and figure a way to put them together and solve a problem or answer a question or make a decision. All right? So that's kind of thinking sideways, or as we say, out of the box. So you got to be able to do that. And so memorize. We're not even close to being done. Don't put your stuff away. Christine, still with me? Okay, you're good. I can see you, but I'm keeping an eye on you though. Getting close to the end of the hour. Now another thing that, this one. We're almost done with class. And this one's been, is it still flicking? No, we'll be done in just a few minutes. You want to come in. Another thing I want to encourage everybody to do is use the simulations that I've mentioned in class and in the annotations. And all those, the one that I mentioned the other day for University of Florida State University, the obnoxious Seminoles, etc. That website's actually pretty nice. And it's got a bunch of different simulations. You can just explore around in there, see if you like something. What are you smiling? Do you like the Seminoles? Good. 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 I saw somebody over here smiling when I mentioned the Florida State Seminoles. That gets me a little bit cranky. When I see Olivia? Okay. Anyway, so definitely definitely use those ones from Florida State. Just look around, see if other demonstrations, and also the one from University of Colorado. And those are located in lecture and in annotation. You can see the references to them. The textbook has a bunch of them. Another suggestion, it's up to you what you want to do, but we do have, let's see, Thursday, Friday, Saturday, Sunday, Monday, Tuesday. That's 6 days. We have almost a week to get ready for the midterm. Today's Friday. Oh, okay.
There's like 4 days.
Dr. V. I'll have to slap myself. Okay, so we have Saturday, Sunday, Monday, Tuesday, and then Wednesday. So that's 4 point something days. And if you calculate the index of refraction of that, I'm just kidding. So we have 4 days. Use the discussions. We won't be meeting on Monday because it's Veterans Day. So use discussions as your virtual study groups. It can be, you guys have been slacking in discussions. In discussions. I mean, you're working hard and stuff, but now, my last 2 comments are the absolute most important. Stay alert. In case I say, oh, I really like this problem. If I post something in discussions, oh, this is a neat diagram. You might want to take that as a hint. But my last
Like memorize
admonition,
it or understand it.
think about it. Think. Always, when, hush now. Listen, I'm going to give you a study tip. Olivia's up here saying, oh, should I memorize it? No, don't memorize it. When you're studying, like when you're studying the textbook or studying your lecture notes, always think to yourself, now, how could Dr. B write a multiple choice question about this paragraph? Or how could Dr. B make a true-false question out of this paragraph? Or how could Dr. Brickner make a calculation out of this part of the lecture? And just think that. So that's what I want you to think. And if I say something in discussions that I really like, think, Dr. B's up to something here. Because I get inspired. And I like to share that with you guys. And you guys didn't realize it, but the bonus point problem, I mean, we did it in class. I mean, pretty much. So if you did the bonus point problem, you were, if you understood that, you were golden. Now, but the last thing to always remember, CJ, no matter what, Audley, no matter where you are, Rain, no matter what happens, always expect the unexpected. All right? And you are dismissed. And I'll see. And we got some time, so if you want to come up and talk, you can. Yeah.